The technical report we're diving into today is Step-DeepResearch from Step Fund's agent team. And this paper, right away, challenges a huge assumption in the agentic AI world.
It really does. The assumption that you need, colossal scale to do real expert-level research.
So what's the core finding for everyone listening?
Okay, the bottom line is this. The work validates that a medium-sized model, we're talking 32 billion parameters, can achieve truly expert-level and very cost-effective deep research.
So it's directly competing with the big proprietary services.
It's positioned to rival state-of-the-art systems like OpenAI Deep Research and Gemini Deep Research. I mean, this really forces you to rethink the whole relationship between a model size and actual complex utility.
Okay, let's get into the how. Because they achieve this efficiency not with some complex multi-agent system, which is kind of the standard approach, right?
Right, no external orchestration. Instead, it's a streamlined React-style single-agent architecture. The secret sauce was focusing entirely on internalizing those research capabilities.
And that internalization comes from the training.
Exactly. It's a progressive, three-stage pipeline: mid-training, SFT, and then reinforcement learning. And it's all built on this novel data synthesis strategy based on what they call atomic capabilities.
So breaking down what a researcher actually does.
Precisely. Planning, seeking, reflection, and reporting. They train for those four skills explicitly.
And the proof is in the numbers. It scored, what, 61.42 on the ResearchRubrics benchmark?
A stellar score. But at the same time, it's the most cost-effective solution out there. The inference cost is less than 0.50 RMB.
That's wild. If you can get near top performance for, what, less than a dime, that just changes the entire business model for companies doing this kind of analysis.
Yeah.
So let's unpack the industry context here. The authors note that the frontier for LLMs is moving really fast, way past just conversational bots and into fully autonomous agents.
And deep research has kind of become the new North Star for judging how good these systems are.
The thing I found fascinating is how they immediately clarify this research versus search mismatch.
Yes. Because existing benchmarks, they often just push agents toward simple retrieval. Things like multi-hop QA systems like BrowseComp.
They're basically just testing if an agent can find scattered facts online.
Exactly. It trains the model to be a very, very efficient web crawler, but that's not research.
Right. Finding things isn't the same as synthesizing knowledge. Real research is iterative. It's a long horizon process.
It requires decomposing your intent, using tools over multiple turns, and this is crucial cross-source verification.
And then pulling all that fragmented evidence into one coherent, structured report. If the model can't hold that big picture goal in its head, it's just not doing research.
So to fix this gap, Step Fund reframed the whole problem. They see deep research as a long horizon decision-making problem over a set of these atomic capabilities.
So the goal wasn't to hard code the steps in some external workflow.
No. The goal was to train the model to internalize an expert's cognitive loop so the agent can self-check and revise its own plan as it goes.
And that's what led them to their architectural choice. That streamlined single-agent React design was a deliberate choice.
It was a bet. They put their faith in the refined training pipeline to give the model robust native capabilities rather than relying on the kind of external orchestration we see in other big systems.
Like the multi-step web exploration in OpenAI system or Gemini's dynamic research blueprints?
Exactly. It's an end-to-end play. They're betting that baking the intelligence directly into the model's weights is just more efficient and robust than constantly managing a bunch of external parts.
Okay, so if internalizing intelligence is the goal, how do you actually do that? How do you teach a pre-trained model, which is great at predicting text, to suddenly become an expert decision maker?
That's the core technical hurdle, right? Shifting the objective from just predicting the next token to deciding the next action.
So what was the solution on the data side?
The solution was defining and then synthesizing data around these atomic capabilities. They defined them as these transferable, high-level action abstractions.
And these form a compact action subspace, the atomic.
Right, and the whole synthesis strategy is built around this really tricky balancing act.
You're talking about the two errors they were trying to minimize, right? The pruning and pruning error. Could you break that down for our technical listener?
Absolutely. This is the crucial part. First, they minimize the approximation error, or pruning error. That's basically how much nuance you lose by abstracting a skill into one of these atomic blocks.
So you want it to be transferable, but not so abstract that it loses all meaning.
Exactly. And second, they minimized Turing-Al-Dollar, which is how difficult that abstraction makes the later reinforcement learning stage. They were looking for that sweet spot.
Abstract enough for efficient training, but not so much that the model can't compose the skills into a full research plan later on.
That's it.
Okay, that makes a lot of sense. So let's get into the weeds on these capabilities. Capability I, planning and task decomposition. How did they make sure the plans were actually any good?
This was brilliant. They used a strategy called reverse engineering synthesis. So instead of trying to generate a plan from scratch, which can lead to some pretty weak logic, they took final, high-quality documents like technical reports or academic surveys.
And they worked backwards?
They worked backwards to generate the initial project task and the high-level plan that must have led to that polished document.
That is a clever way to guarantee feasibility, because you know the plan works. It already produced a result. But does that create a kind of echo chamber?
That's a sharp question.
I mean, if you only learn from successful finished documents, how does the agent learn to handle a totally new or ambiguous task where the path isn't clear?
So they used this method to establish a strong initial logical constraint. Think of it as the backbone of expert feasibility.
Foundation.
The foundation. And then later stages, especially the RL phase, that's where novelty and stress testing come in with tool failures and real-world noise. But they had to anchor that initial planning in just extremely high feasibility and logic.
Got it. Okay, on to capability 2, deep information seeking. This is where we move beyond simple Q&A.
Right. They did this using graph-based synthesis. They'd take knowledge graphs like Wikidata 5 meters and CNDBpedia and do controlled subgraph sampling.
Using non-generic entities as the starting points, the seed nodes.
Which forces the agent to navigate these complex, multi-hop paths to find an answer.
But those knowledge graphs can get outdated fast. How did they make sure the data actually reflected the real world?
That's the key. They did verification. For every single triplet they sampled from the graph, they ran an external search to verify and expand on that info before generating a fuzzed, complex question.
And they had another layer of quality control too, right?
Yes. Difficulty filtering, this is a great detail. Any query that could be solved by a weaker base model, a QWQ32B, using the standard React framework was just thrown out.
That's a great way to ensure the training set is actually hard and teaches advanced skills, not just baseline retrieval. Okay, what about self-correction? Capability 3, reflection and verification.
Yeah, this is where the rigor comes in. They train this using what they call the error reflection loop.
So if the model's initial plan fails,
say it gets an irrelevant search result or there's a logical inconsistency, it's prompted to perform a reflection action. It keeps its historical memory and then retries the step up to 3 times.
So it's literally teaching the model to pause, check its notes, and rethink its assumptions, building introspection.
Exactly. And that internal loop is then backed up by external rigor. They used a deep verification workflow.
Multi-agent teacher system.
A multi-agent teacher, yeah, to simulate human expert review during data generation. It had specialized agents for extract, plan, verify, replan, and report. It just ensured every training trajectory was logically self-consistent and fully backed by evidence.
That sounds intense. Okay, finally, capability 4, report generation. This is more than just spitting out an answer.
Way more. The SFT phase focused heavily on strict instruction following and formatting. They even explicitly included professional citation formats, like the cite command, in the data.
Which does 2 things, right? It makes the output traceable.
And it teaches the agent to prioritize grounding its claims in evidence over just being fluent.
So those atomic capabilities are the data building blocks. Now, let's look at how they orchestrated them in that 3-stage progressive training pipeline. Mid-training, SFT, and RL.
Right. Stage 1, agentic mid-training, used the Quen 2.532B base model. And this phase was all about curriculum learning.
They started with a smaller context window and expanded.
Exactly. They progressed from a 32K context, which was focused on just injecting the atomic capabilities, up to a 128K context.
And the longer context helps with what?
It strengthens those crucial long horizon behaviors. Complex retrieval, planning, and importantly, explicit tool invocation logic across longer and longer research tasks.
And the performance gains showed this was working, especially on structured reasoning tasks like frames, which jumped by almost 11%.
Yeah, it confirmed the agentic training was hitting its mark, not just making the model a better generalist.
So that's the prep work. Then stage 2, supervised fine-tuning, or SFT.
Here, the focus shifts to composing those atomic abilities into efficient, end-to-end trajectories. They use their big deep search and deep research data sets, but the key strategy was something they call trajectory efficiency optimization.
Meaning they only kept the best paths.
The correct and shortest paths.
That's so smart. If the model learns to succeed in fewer steps, it's just inherently more efficient and cheaper to run. Was that a big driver of the cost reduction?
It was one of the primary drivers of that final cost efficiency. By optimizing for shorter, correct trajectories, they immediately cut down on the number of API calls and model steps per task.
And they also built in robustness against real-world messiness.
They did. They intentionally injected structured noise. They kept a small number of trajectories that had real-world tool call errors, like an empty search result, but were followed by a successful reflection and correction.
So the model learns not to panic when the web doesn't cooperate.
Exactly. It prevents it from just collapsing when things get unstable.
Which brings us to stage 3, reinforcement learning. This is where they optimize the agent's behavior in a real tool use environment. How on earth did they design a reward function for something as subjective as research quality?
They used a rubrics judge, which was trained on scores from a strong model, but the real innovation, I think, was the asymmetric binary mapping of the reward signal.
Okay, what does that mean?
Well, they realized the standard 3-part judgment satisfied, partially satisfied, not satisfied, was actually too noisy for effective training. That middle category, partially satisfied, was the problem.
Why was that 0.5 reward so disruptive?
Think about it. If you give the model partial credit, a 0.5, it learns that its effort was just.
Okay.
But it has no idea why it wasn't a perfect score.
It's an ambiguous signal.
A very ambiguous signal. I did sort of well. Slows down learning and creates these unpredictable optimization paths. So they converted it to a binary signal, a 1 or a 0, based on the rubric.
So for a positive rubric, you only get a 1 if you are fully satisfied. Anything less, even partially satisfied, gets a 0.
Exactly. By mapping the B's and C's all to 0, the model gets this crystal clear signal. If you aren't perfect, you failed.
Which forces it to optimize only for the fully expert-level trajectory and converge much faster.
It gave it a very clear, distinct optimization direction. And for the algorithm, they chose PPO with generalized advantage estimation, or GAE.
Over a critic-free method. Why was that actor-critic structure so important here?
Because in a long, complex task like generating a research report, a single reward at the very end isn't enough. The learned critic in PPO provides reliable token-level value estimates.
So it's getting feedback on the intermediate steps.
Right. It provides actionable learning signals for decisions like which retrieval strategy to use or which piece of evidence to select. It just makes the whole learning process much more stable for these long-horizon tasks.
And that really comprehensive pipeline paid off. Let's look at the evaluation. They used the established ResearchRubrics benchmark and also their new ADR-Bench.
Right, which is a Chinese benchmark with 110 queries focused on really realistic scenarios and things like law and finance.
So what were the headline results?
The results are pretty striking, especially when you look at performance versus cost. On ResearchRubrics, Step-DeepResearch scored 61.42.
Which is very competitive. It surpasses systems that rely on that complex orchestration, like OpenAI Deep Research.
And it significantly outperforms leading open source React agents, like Kimi K2 Thinking, which you might remember is often based on a much larger 65B model and scored 56.17.
So that just highlights the architectural win. Better performance than larger or more complex open source agents while competing directly with the closed giants. And again, the economics are the game changer.
Less than 0.50 RMB per inference. That is dramatically cheaper than the commercial systems. Gemini Deep Research is about 6.65 RMB. OpenAI is around 5.32 RMB.
So they're getting near top performance at basically a tenth of the cost.
It's the high efficiency frontier for agents. And if you dig into the detailed metrics in Figure 8 of the paper, you can see exactly where that atomic capability training paid off.
Okay, where did it shine?
It led significantly in implicit criteria, which measures the model's grasp of underlying logic and self-consistency. It scored 54.5 there.
Which points directly back to the reflection and verification training.
Absolutely. And their focus on rigor in the data synthesis clearly worked for evidence grounding. It tied for the top spot in citation quality, with Gemini Deep Research scoring 57.0.
So that SFT phase for professional formatting really paid dividends.
It did. And it also scored highest of all in communication quality at 58.2. So the reports aren't just factually grounded, they're actually clear and readable. They don't just stack up fragmented bits of information.
But it's not perfect. What were the limitations the authors themselves pointed out?
Well, the model showed room for improvement in really high-order reasoning domains like advanced STEM and philosophy. It trailed Gemini deep research in those specific areas.
And they think that's a scale issue.
They're pretty frank about it. They attribute it to the inherent complexity of those frontier knowledge areas, suggesting there's a constraint tied to the 32B parameter scale for those very demanding domains.
So there's a limit to how much intelligence you can internalize at this size, at least for cutting-edge science. But the overall architectural bet paid off. The ablation study confirmed it.
It did. The full Step-DeepResearch model consistently maintains a higher win rate against a version without the mid-training and against commercial competitors on ADR-Bench.
Which just validates that this end-to-end capability-focused training approach is superior to just scaling up the model or relying on external workflows.
It proves that strategic data construction trumps raw scale, at least up to a very, very high level of complexity.
So what's the big takeaway here? This paper gives really compelling evidence that strategic data design and a progressive pipeline can optimize a medium-scale model, a 32B model, to not just approach, but in many key ways exceed the performance and cost efficiency of much larger systems.
But despite that massive success, the authors are very honest about the challenges that still need to be solved for, true commercial deployment.
What are those?
They mention brittle tool use when APIs change, the difficulty of maintaining factual correctness in a really noisy web environment, and the need for greater report auditability.
Making sure every single conclusion can be traced back to a specific piece of evidence.
Exactly. Those feel like the final hurdles for truly reliable production-grade agents.
So what are the next steps for this research? If they've pushed the single-agent paradigm this far, where do they go next?
Well, the path forward seems to be moving toward what they call collaborative intelligence. They recognize that to tackle those complexity limits in STEM and philosophy, you're going to need a division of labor.
So a multi-agent system.
Exactly. They plan to introduce a multi-agent paradigm with specialized roles planners, retrievers, verifiers, writers, all working together.
And the key innovation there is how they work together.
Yes. The critical part is using consensus mechanisms between these agents to reduce hallucinations and ensure stability. It's this acknowledgement that while internalization is great for cost and efficiency, distributed processing through consensus might be what's necessary to solve the hardest frontier knowledge problems.
And to push past the inherent constraints of a single 32B model.
Right. And that's a key thing for you to think about if you're working on agent architectures today.
Absolutely. Thank you for tuning in to our analysis of the Step-DeepResearch technical report.